Everyone, in this video we're going to go through some extended response questions from exam 2. So you're allowed your bound book, you're allowed your calculator. Just before we make a start, I'm going to go through what you would do during reading time. So there are students who do start with the extended response first, I guess, because with your multiple choice, if you don't get them all done, you've got a 20% chance of still, not 20% anymore, it's 25% chance of still getting it right if you guessed. So during reading time, I would probably start with the extended response, but think about how you're going to approach them. So you've got 15 minutes. So with a lot of these questions, we use the function over and over again, so you can use define in your calculator. Now, sometimes that's more time consuming than needed, but that's why during reading time, it's probably a good idea, is it worth actually defining it in my calculator? So for this very first one, I'm going to show you how to use define. Hopefully it's not the first time that you've seen it, but perhaps a reminder of how to use it. All right, so an amusement park is planning to build a zip line above a hill on its property. The hill is modeled by this function here from 0 to 30, where x is the horizontal distance in meters from an origin and y is the height. All right, beautiful. So the very first question asks us to find the derivative. It is only worth 1 mark. It is a tech active exam. You just do it straight on your calculator. So let's go ahead. I know you know how to do this on your calculator, but let's define this function. So f of x, is equal to, and what do we got? 3x times, and I'm doing this on my keyboard, but you can just use x down here on your calculator. 2000, and that is it. Just make sure we haven't forgotten anything. I always like to do it, especially because we've defined it, so we've got to make sure it's all correct. All right, and then the calculator says done. So if we want to find the derivative, you can go interactive calculation and diff, and then you can just do f of x that way. Oh, come on, why are you doing that to me? That's very annoying. All right, I don't know why it's done that. That is so frustrating. All right, let's do it the other way. Probably good to show you. Oops, don't want that. Oh my gosh, I haven't made it. Oh my gosh. All right, this is where I've already cleared everything. Why is it not working? Maybe it wants a times in between. Yeah, there we go. All right, so probably good to show you that because if this happened to you in an exam, you would probably be freaking out and be like, oh no, now I have to do it by hand. All right, so the calculator often likes a multiply sign in between your variables, and so between variables, so if we had another letter there, you'd put a multiply sign, and the brackets. So I think if I use just normal x, like this x here, it probably wouldn't care. So let's just actually try that and see whether it cares or not. Yeah, so it didn't mind me using this other x. See how I got rid of the times, but because I used the keyboard, it wanted to multiply. So probably not the best start first question to have that sort of not work, but you have to also troubleshoot when the same thing happens to you. So just remembering to use a multiply sign. All right, so moving along. State the set of values for which the gradient of the hill is strictly decreasing. Now, this question was not answered well, so I've got a little note there which we'll go through in a second, but I'm just going to explain what the question is asking and where students went wrong. So we're looking at where the gradient is strictly decreasing. Don't get decreasing mixed up with negative, all right? It's where it's decreasing. So if you think of the rate of change, it's slowing down. So if we have a look at the gradient function, so let's go on to our calculator and actually sketch it, because we're talking about the gradient here, not the original function. So just going to our graph, and I've got f of x written there already, probably from a different question, but that's okay because I defined it and we can't see too much there. So when you can't see much on your screen and you've been given a set of axes, do change it to suit what the question says. So we're going from 0 to 30, and then from 0 to 10. You can go slightly out, but we can just do that. All right, so that's our original function. If we want, so we need to actually sketch the derivative. So I can just go, all right, I want to sketch the derivative. So I can just type it in here. I don't need to retype all this because I've defined my function. My calculator knows what the function is. So now I can just plot that. And the reason we can't see it is because it's below the axis. So I can just lift it up to see. All right, so you can see so this is the gradient function now. It is strictly decreasing as we go down here. All right, it's decreasing, and then it's hit 0, and then it's increasing again. So if we want to figure out where it's strictly decreasing, we need to figure out where this stationary point is of the gradient function. So you can just go analysis, gsolve, and we want the minimum value, so function min, and we can see it's there at 20. So because it starts at 0, so it's going to be from 0 to 20, it's strictly decreasing, and then from 20 to 30, it's increasing. Now, in terms of your bracket, so this is why it was also not done too well. So your gradient, you can't take the gradient at the end, at an end point. So here at 0, we actually can't take the gradient because we don't know what's happening before it. So it's not included, but the 20 we know what is happening after it. So I'm just going to show you what I've written here, and I wrote this a while ago, so let me just think. So question B is asking where the gradient, and my son's just got home, so he's going to open the door and say hi. Where the gradient is strictly decreasing, not where it is negative. So remember I said that before. So sketch the graph of the gradient function, which we just did. X equals 0 is not included at as gradient, I should write. It doesn't exist at endpoints, but x equals 20 is included as gradient exists at this point. Note also that x equals 20 is a point of inflection. So if we have a look at this graph, it's concave up until we get there, and then concave down. All right, so not done well with the brackets for that question. All right, moving on to the next one. So the cable for the zip line is connected at the origin at a height of 10 meters and is straight for x between 0 and a, where a is between 10 and 20. So that's important to note later on because we do, I think, solve for a. The straight section joins the curved section at point A. The cable is exactly 3 meters vertically above. All right, at some point between A and 30. Okay. All right, state the rule in terms of x for the height of the cable. So this is the cable above the horizontal axis. So note how it's the same distance. It's 3 meters each time. So you just take your function for the hill and it's shifted up 3. All right, so it's just plus 3. Nice easy mark. All right, find the values of x for which the gradient of the cable is equal to the average gradient of the hill for x between 10 and 30. So the gradient of the cable we did up here. All right, so the gradient is the same, so it's up here. And then we had to find the average gradient. So just doing your average rate of change from, oh, I did that around the wrong way. Let me just change that. Oopsie, oopsie, doopsie. All right, so just had these around the wrong way. So that should be 30 and this should be 10. All right, so we just then make them equal each other. So it was worth 3 marks and I'm like, oh gosh, I need to show a bit of working. So 3 marks, so I got my average gradient -3 on 10, that's probably 1 mark. I'll let my gradient equal -3 on 10 and then I just wrote it. I don't know why, probably because I felt like I needed to do something for 3 marks. I feel like this was an easy 3 marks. And then it does say values of x, so we do get 2 values of for x. And then we could just leave it like that. It doesn't say to round it at all, so just make sure you leave it in exact form. You don't really need to go on and simplify that at all. You will notice in the assessor's report it might be written slightly differently, but these, it hasn't asked for a specific form, so we can just leave it like that, is fine. All right, the gradients of the straight and curved section of the cable approach at the same value x equals a, so there is a continuous and smooth join at A. So when it's continuous and smooth, it just means you have the same gradient at that point. So if we're stating the gradient, all we're doing is substituting A into our gradient function, another easy mark. And the thing with methods is sometimes we overcomplicate it or overthink it, and you can see how you're probably seeing like, oh, is that it? Is that all I had to do? So if you got your gradient function back in, I think it was the first question, all you have to do is substitute in A. All right, find the coordinates of A with each value corrected 2 decimal places. All right, so it's worth 3 marks, so I'm just conscious I have to show a little bit of working out. All right, so they didn't use f of x or g of x. They used, why have they used hx? Anyway, I defined, I don't know why I said f of x when that's still hx. Anyway, so I just defined 2 functions. So we've got here f of x, which is same as h of x, it looks like. I did this a while ago. Sorry, I'm just, yeah, exactly the same. Don't know what I'm doing. All right, and then g of x is the straight line. So we know the equation of a straight line is y equals mx plus c. So that's all that is, the mx. M is your gradient, and 10, if we go back up here, we can clearly see is the y-intercept. So where m is equal to the gradient of f. All right, so the gradient is the same there. So I let the 2 functions equal each other, because remember they're smooth at that point, and when I solved for that I got x equals 11.12. so I might just show you on the calculator. Sorry, I'm doing all this work and you're probably thinking, what is she doing? All right, so we've moved on, haven't we? No, it's still the same question. All right, so we've defined f of x. So f of x was the hill. All right, so let's all right, so I've got a different hx. Maybe I should change this from fx to hx just to make it a little bit more straightforward. I don't know why I did. There we go. Let's just change that. Yeah, because hx is this line. Yeah. Okay. Hold on. Sorry, I'm probably giving you, no, I was just making sure hx hadn't been defined. I called it hx, okay. Doesn't say that I have to, I just called it hx, h for height. Maybe, I can't remember, doesn't really matter. All right, and that's h. Okay, so what we can do is define again. So define, and h of x is equal to f of x plus 3. Right, because remember back, sorry, I'm giving you motion sickness. Here was our original function and we're just adding 3. So remember we already defined that up here. Right, so there's our function and I've just added 3. So to give us hx. All right, and now we're going to do g of x. I'm going to define that. Define g of x is equal to, so remember the gradient is my m. So on my calculator I can just go, all right, here's my gradient function. So the derivative of f of x times x, right, because remember mx, so dy dx is my gradient, plus 10. All right, so there's hx, there's gx. I probably should have written them down. And then I just let them equal each other. So we can go solve, and I'm going to let hx equal gx. And we get that, and we're like, oh, I've got to take it out of standard mode. All right, and we get different x values. So remember, we do have a set domain, so we don't want this first value, so we're taking this second value, and then A was between 0 and 20 or something from memory, or 10 and 20. All right, so we can't take that value there. So 11.12 is our X value. So remember, we're doing it to 2 decimal places. So not the exact value for this one, we saw it before. So then we just have to let X equal 11.12 and then substitute that back into either HX or GX, and we get 8.95. So on the calculator, I could just go H of, oops, that's not an H. H of this, I can just highlight it. All right, and we get the 8.95. So defining it is good as long as you know what you're actually doing. It saves so much time. So what I've done here, g of x equals mx plus 10, where m is the derivative of h of x. I don't have to write what the derivative of hx is because it's going to take up too much time. I've already defined it, so I can use this notation just to help me work through that question. So being worth 3 marks, you do have to, I mean, obviously you can do a lot on the calculator, but you do need to signpost it as you go along. All right, find the value of the gradient at A correct to 1 decimal place. So let's just change that from F, although the gradient of F is the same as the gradient of H, which is the same as the gradient of G at that point. So on here we can just do the derivative of, oops, dx of hx, and then we can just say, all right, let's, oh, I could probably have done it there. Given that x equals 11.12, and we had to do it to 1 decimal place. So you can do your derivative like that, or you could go interactive calculation diff and just do hx and then a derivative at a value and do your 11.12 there. Oops, and you can get the answer that way. All right, moving along. So 2019 exam 2 question 3. So we've got some trig happening here. So during a telephone call, a phone uses dual phone frequency electrical signal to communicate with the telephone exchange. All right, the strength of a blah, blah, blah is given by this function. Okay, where t is a measure of time. So this is just a sum function. So what it means by a sum function is you got one function added to another function. And here it is, the graph. All right, state the period of the function. So when you've got a sum function like this, or it could be a product function or a difference function. So product just means it's multiplied, difference is subtract. A period is just when the pattern starts and finishes. So I've highlighted it there in pink. You can see that it ends at 12 and then it repeats itself. All right, find the values of t where f of t equals 0. So that basically means your x-intercept, but we're only going from 0 to 6, but including. So an easy question. We're going from 0 to 6, and we've got 0, 4, 6. When I first did this, I kept doing all of them, and I was like, oh, this is so time consuming. Why would they make me do this? And they did make me do it. I just didn't read the question properly. I had to make sure I was going from 0 to 6. All right, find the maximum strength. So this was easy. You can just put this into your calculator and do max. So calculation. So because it doesn't go up to infinity, so we can just go function max and then type that in, and then you'll get it that way. I'm not going to do that because I want to move along. It wasn't a difficult question. All right, the wind speed at a weather monitoring station follows this function, Vt, where V is the speed of the wind and T is the time in minutes after 9 a.m. I don't think that I needed to know that. Anyway, I haven't also given you all the questions, so that could have been important later on. What is the amplitude and the period? Oh, you'll be like, easy 2 marks, like during reading time. You should be like, yes, I can do that. All right, you've got your bound book. You can do it in your, if you forget. You can look at your bound book. So amplitude is just what we're multiplying sine by, which is 16. If it's negative, remember it's irrelevant. It's always, amplitude is always positive. And your period is 2 pi on n. So n in this case is pi on 14. So you get 28. The 20 is irrelevant. Just the plus 20 does not change your amplitude or your period. All right, what are the max and min wind speeds at the weather? So basically it's asking for the range. You could do, like I just showed you before, you could go interactive and calculation and do your max min that way. Quite a time consuming, and I love doing the range of trig functions like this. So a sine or cos function goes from -1 to 1, and just think about the transformation. So this 16 is a dilation from the x-axis, so we're multiplying it by 16. So you think about it anyway, your amplitude is amplitude is 16. So if we didn't have this vertical translation, it would be from -16 to 16, but we do have that vertical translation, so it's plus 20 plus 20. So our range is 4 to 36. We can't leave it like that. We do have to actually say what the max and the min is. Actually, I think they would accept that. That would be a bit harsh if they didn't. But your max is 36 and your min is 40. You should probably state it. Just why risk not getting that easy mark? All right, next one is so easy as well. Just making sure you do it to 4 decimal places. So you've got the function and you're just substituting in 60. Making sure your calculator is in radian mode. All right, part D is the average value. So we haven't done this yet because we haven't done anti-differentiation, but the average value function formula is on your formula sheet, and this is exam 2, so it'll be in your bound book. But I've just written it there, and then we just substitute in A and B. So A and B, A is your lower limit, B is your upper limit. So your lower limit is 0. So you can see I've substituted that in for A. And B is your upper limit, which is 60. So just doing that straight on the calculator, and you get 20.45. Didn't even need to convert it at all. 20.45. Beautiful. All right, moving on to 2020 exam. So this is question 1. Nice question to begin with. So it's a show that question. In a show that, you should pretend, I don't know what that answer is. Just pretend it says, what is the value of A? You do have to show some working out though. So I think they would look for f of 0 equals 4, and then I did the substitution and then a bit of a calculation to get that 1/4, but an easy mark there. Often show that questions are given to you so you can use the answer later on. You're not, because if you kept it with A, you didn't know what it was, then you couldn't really go any further. And then all we had to do is expand this bracket. So I was like, really? Oh my gosh. So let's get out of that. So you can just go transformation, expand, and type in the expression, and it'll expand it for you. You don't even have to do that by hand. Easy. It's only worth 1 mark. I did write plus -2. I don't think you'd be penalised because there's nothing wrong with that. I just left it because then I realised B was -2. Yeah, moving along. All right, so now we've got the gradient function. So remember, this is a quartic. So the derivative of a quartic is a cubic. And so an easy mark, we're just finding the derivative. So you're given the actual function in part B with the quarter on there. Then you expanded it. But remember, you've got your calculator. You don't even need to, it's probably an easy one to find the derivative, but you could use your calculator. So x cubed minus 4x is this one here. I actually, before I started, was thinking, I've got to use those 3 points. And I'm like, hold on. What information have they given me? And then I realized, they've actually given us the function of the original graph. So I can just easily find the derivative. All right, find the minimum value of the graph of the gradient on the interval from 0 to 2. So basically, we've got to find this point here. So if we're using the correct notation, we're actually finding the derivative of the derivative of the gradient function, which is your second derivative. So we go f dash dash. All right, and then we let that equal 0. So just like we would for any stationary point, we find the derivative. So we're finding the derivative of the derivative. That's why I've got the dash dash there. Now, the second derivative is not on the course, but there's nothing wrong with using it, and it's easy. So you may as well, realize that it does exist. So that's at x equals 2 root 3 on 3, but it is asking for the minimum value, not the value of x. So we do have to substitute that back into our gradient function, into this cubic, to get that. So not just the x value. So that's probably 1 point and then 2 points for the actual answer. All right, and then this one was nice and easy too. So we just had to state what transformations there were. It's probably a good idea to stick with dRt, so no dilations we can see, but there has been a reflection, so it's been reflected along the x-axis, and then it's been shifted up. You could have also said it's been shifted down and then reflected, but it's easier if you stick to the dRt, and then you won't get confused. But you could have had it if you did your translation first, so it actually shifted down to, and then it was reflected. But I would say most students wrote those two, because transformations, you can get to the same point many different ways. All right, last question. So I think this was from the same exam, just a bit later, question 4. So we've got this function, and it's sketched for us between 0 and 3. Find the slope of the tangent. And I'm like, what? Okay, that's pretty easy. So on your calculator, we can just go interactive calculation and line and tan line. And then we just write the expression, and we want it at 1. Oh, excuse me. Now, when we do that, and I might actually do that to show you, I should have defined it. I was just thinking before, should I define it? 1 minus x squared, close your bracket, and we want it at 1. So it gives you the equation, but it's actually asking for the slope. So if you gave the equation, you wouldn't actually get the mark, because you haven't answered the question. So even though you're given the tangent equation, and obviously a part of that is the slope, it's kind of like, well, why should you get the answer? Why should you get it correct and someone else also get it correct? But you wrote the equation and they actually answered the question. So they wouldn't mark it correct if you gave the whole equation. You actually need to answer the question, so it's just -2. Part B, find the obtuse angle that the tangent to f at x equals 1 makes with the positive direction of the horizontal axis. So whenever you see an angle involved, and when we're talking about tangents and gradients, that's when you will see it. Nowhere else. You need to have your calculator in degree mode, all right? So we're measuring an angle, so it has to be in degree mode, and your tan is, all right, so just a quick recap. So tan theta is equal to m, all right? So tan is equal to opposite over adjacent, which is your rise over run. All right, so if you've watched my video on tangents, I go through that. So if that's new to you, maybe you haven't watched the tangent video. All right, so we just so we're just solving for theta. So inverse tan, where are you, of -2. Now, obviously we can't have a negative theta, but that's okay because it's only worth 1 mark. So we want the obtuse angle. So this is not an obtuse angle. So we're just going to do its supplementary angle. So supplementary angles add up to 180. So we just go 180 minus that 63, blah, blah, blah. And that's where the 117 comes from, because it's to the nearest degree. So always make sure you're rounding. A lot of rounding in these questions. So just making sure you round to however many decimal places it asks. All right, find the slope of the tangent to f at point x equals p. All right, so we just take the gradient and substitute in p. So I took the gradient of this function and just substituted in p, which is there. It's that easy. All right, so the slope is your gradient function. At a point, the gradient function has the same gradient as the tangent function, so that's why we can just find the derivative of f and substitute in p. So there it is. I know I'm working quite quickly. I didn't want this to actually go so long. Find the value of P for which the tangent to f of at x equals 1 and the tangent to f at x equals P are perpendicular to each other. So perpendicular means they meet at a right angle. So remember on our course, we don't refer to them as normals. Tangents, we do have tangents, but normals, we do just say it's perpendicular, but they're actually at different points. All right, so they're not intersecting at x equals 1 and x equals p. They're two different points clearly, because one is 1 and one is p. So at x equals 1, our slope is -2, which we found back in the previous question, which is a bit annoying because if you didn't get that, then you couldn't really do this question either. At x equals p, because it's perpendicular, we take our negative reciprocal. So we just, if one slope is negative, then the other one's positive. And what it means by reciprocal is we just flip it. So the number 2 is just 2 over 1. So its reciprocal is 1 over 2. All right, that's what it means by the negative reciprocal, but that shouldn't be the first time that you've seen perpendicular lines. All right, so then we just let our our derivative at p equal 1/2. So we did that in the previous question, and you can do that all on your calculator. I would probably have defined that and done all this work. So if you haven't done this question, go ahead and define it and work through it. All right, and we're doing it to 3 decimal places, so we get p equals 0.655. Now, if you're like me and you can't be bothered going to get p through the ABC, don't go to var, use ABC. And you use X, Y, or Z, just make sure you don't write X equals, because you would get it wrong. All right, it's P, so always use the letter. If you think you're going to use the wrong one, just be consistent with the paper and use P. All right, then part 2 of question D is worth 3 marks. Oh my gosh. All right, let me rethink this question. All right, find the coordinates of the point where the tangents to the graph at x equals 1 and x equals p intersect when they are perpendicular. Give the answer correct to 2 decimal places. So I remember this one, it took me a while to think about it. So I just started and thought, well, tangent lines are straight lines. So I just thought, well, let's think about what I know. So my first tangent I knew was -2x plus 4. Remember, I found that on the calculator up here. So I wrote that down, and then I thought, well, what about my second tangent? I know it has a gradient of 1/2. So I wrote 1/2x plus c, and then I'm like, okay, I need to work out what c is. So my equation is y equals 1/2x plus c. So the point P is on my second tangent. So I substituted that in. So P and f of P. So P being 0.655 and f of P, when I substitute in 0.655 into the function, I get 2.319, and then solve for c. So that's the equation of my second tangent. And then I was running out of room, and I was like, oh gosh, all right. Yeah, I probably needed a bit more space. Then you can just let them equal each other. So -2x plus 4 equals the other one, so 0.5x plus 1.99 comma x. So that's the first point. It only has to be to 2 decimal places. Now, just making sure you realize it's the equation of the tangents, not the equation of the original function. So to get this 2.39, the corresponding y coordinate, you just have to substitute it into one of the tangents, doesn't matter which one. So let's do. So we can take the 0.8 times that by -2, and then plus 4 will give us our, yeah, we probably shouldn't have rounded 2.39. So if I did all this, which I did on a different calculator, I wouldn't have just done 80. I would have had more decimal places. So just make sure you do that, which I did do when I did this question. But if you rounded, you wouldn't get 3 marks. So just make sure you work through and don't do any rounding. So all these answers, I would have my would have in my calculator, and I would just drag and copy it down. So for the, I don't know, there's not really any examples there that I would use because I've just been talking about them. All right. Thanks everyone. Bye.